well prepared, but I could not fit. I could not work from the day after on a Formula One car or parts of cars. And my time came in 2000. They had more time. They wanted to substitute this guy, exactly the one they hired in 1997. And yeah, in June 2000, so now more or less 25 years ago, I could join Ferrari. And this was the state of the art of the finite element models. So not so fine mesh, so elements are quite big. What you see here, all colored, are everything, single color is a property. It's made from composites, carbon mainly. And the difficulty here was that there was still the zone method, which was used to prepare the properties of each of this part. This means that you have to manually build up your sequence of lamination with the laminate for every one of these. And maybe the first time it's easy in the sense that you know exactly what you want. But if you then need to change a ply, which is common to this, and this, you need to go in each of the single and add or take off one of the plies, and you have to do it in the right order. It's easy to make mistakes, of course. So you need a lot of concentration, and it requires patience. And in Formula One, you don't have patience because you need to produce results in quick times. Computational power were what they were. There was no parallelism. So it was one CPU. They were starting in those days to have Nastran for more CPUs. And in our days, this thing is made easier. It's the ply-based approach is used. So you just define your sets there where you want to apply the ply, exactly as if you would do in production. You have your mode, and you place your ply where it has to be. And then it's the software that still converts this information into the ply-based. So here is an example to show the torsional behavior, because torsional stiffness of the monocoque is one of the requirements for Formula One and is one of the tasks that a stress engineer in motorsport is asked to do. Load is introduced through the suspension. And you see here the suspension is done with one-dimensional elements, beam elements, and somehow connected to the proper points on the monocoque. Non gira. Magari le puoi vedere. Se no lo facciamo così. A mano.
Ce la facciamo.
Sì, ce la facciamo. In qualche modo. This is the so-called roll-up. So it's the part that stays behind the driver head, which has the task to get the air inside the engine and for maybe cooling some stuff, and to protect the driver in case of a rollover of the car, so to protect the driver head. This is coming from 2006. It's from a car that never saw the light. It was a project from Dallara, which was supposed to design the car for Midland, which was then bought by Jordan, which then became Spikers and whatever. I don't even know now what is the team. I need to think more than that. And you see, this is the failure index. So it's a sort of contour like the von Mises stress, but for composite structures. It means that when you have one, it's failing. So you would like to have everything which is below one. Sometimes in case of this kind of structure, I will tell you a little bit more how it's done. You can maybe tolerate some more than one, because you can tolerate some failures in some areas. So the regulations from the FIA, they say that it has to resist and up to a certain quote altitude, well, set quote, the part can be damaged. And here you apply just some load. It increased that load during the years, and now currently is 160 kilonewton applied in a given direction, so with some components along X, along Z, and along Y. And you have to repeat it also from the rear. It's quite hard, this thing. And because it's on top of the car, okay. With the mouse, it's working. Because it's on top of the car, you would like to have this part as light as possible, because by having it heavy on the top, you will rise the center of gravity, and it's something that you prefer not to do. So you try to really be at the limit. This clearly failed. And you see it's cut. And this thing, it was solid carbon. So this is something like 22 millimeter thick. Each ply is 0.2. So you can imagine how many plies, we can calculate how many plies to go in there. And then we have some cores here. Honeycomb, this is Nomex. So it's an honeycomb made out of paper, cartoon. This was clearly cut after the test, but you see here it's when it was applied, and clearly you see heavy damages. So the calculation showed that it should have been not a so disaster in terms of failure, but actually it didn't even reach the value that it was supposed to reach, so it failed before. And this, we realized later, when additional computational time and kind of elements were available, it's shown here, where we reach more than 1.5, same failure index, the same kind of failure index. This was done using a 3D element. It's only one in the thickness, but each of these elements can get the description of the laminate as if it was a shell element, like the one before, so a plate element. But this can reproduce in a better way the geometry, so the high curvature there. It's still not ideal, because you would like to have more, of course, more elements in the thickness, but this one already gave the indication that that model, the previous one, the one which was used and it was the only available, was not giving the right results. So even having a higher margin, maybe 1.2, 1.3, would have not been enough, because here we see we are above the 50%. More recent times, and you see we can place also part of the monocoque. We can simulate bonding here. So this part is made out of aluminum, rapid prototyping. You see here clearly the displacement. Here is the from stress, even if we allow for plasticization of the material, because still regulation says that you can have damages up to a certain Z. And here is the damage in the glue. So you see at a certain point it starts failing, and then the failure progresses until the completed bonding. And see here, you see the graph, you have different steps. So the loads come to a certain point. This was at the really beginning of the design. So it was the first steps doing with this strange shape, very triangular, very sharp triangular shape, which was wanted by the aerodynamics. So then the philosophy changed, still made with rapid prototyping, but with some sheet metal approach, like if it was a boxed structure. And it was what was on the car. So here, up to now, we talked about strength. The stress engineer needs to guarantee that the structures that are designed and then produced can resist the loads that are foreseen. In that cases, they were the one provided by FIA, so the regulations say you have to apply this load. Of course, you have to do still, the test is still there. They don't rely on calculations. It's you that you iterate until you think you are confident, and then you go to the test. You produce the part and you go to the test. But there are some other, at least one other thing that a stress engineer has to look has to fulfill the requirements that here is asked to, and is stiffness or compliance. So minimize or maximize compliance or stiffness depending on what the part is. So here we are looking at, again, very old models from the front suspension and the rear suspension. Don't care about these elements, which are, again, beam elements just to properly constrain the two upright. This is the so-called upright, which is carrying the wheel bearings and the hub where the wheel is attached. The wheel here is schematized with a rigid element to the contact patch, where the tire is touching the ground, and where the forces for the suspension are introduced. So those things need to clearly resist to the loads that are coming from vehicle dynamics models, which are compared with the telemetry data, of course. And so the structural group in general gets a set of loads from the vehicle dynamic group or from the track. And the design is done on those, which are in general the envelope of all the tracks, et cetera, et cetera. So there is already a certain safety in the loads that you get. Here, I'm sorry for the very nice drawing here, but I'm showing here a ball joint. So it's an element which allows the free rotation, of course, and restraining the translations, and is used to connect the wishbone, so the elements of the suspension, to the small block. And it has this behavior. If you test that thing from minus to plus forces, you see that when it's changing the sign of the load, you get a huge blade. So this is the displacement. And this clearly is giving a loss of stiffness, which is, for us with driving normal cars, is not a problem, of course, but for drivers, it can be something they feel, and the softer the car is, the least reactive is. So you need to have something, and then it's the driver that knows how to use the reactiveness, say that, of the car. So mid of 90, something like that, John Barnum, who has been also designer for Ferrari, invented this system. So instead of having the ball joints, he said, why don't we put flexible elements? They're called flexures. So here we have a normal bolt, strong one, so we don't have the ball joint, and we do have those things, at least on the input side. The output to the connection to the upright is still done with ball joints, but you get rid of some of those compliances. But clearly this is a problem because you want to have it soft in bending to allow the suspension to move, and you want to have it stiff actually because you still want these elements to be stiff. And also because this is introducing a potential instability problem. So you need to balance out. First one was made out of titanium. This is, again, one project that didn't see the light, and they were all machined from titanium plates. They were costing a lot. Luckily, they never went to the car, to the truck. But then, why not using carbon? Because with carbon composites, you can place the stiffest materials at the neutral plane of the bending. So actually they will work, but they won't work that much in bending. So you start compromising and using carbon. But of course, having huge deflection, carbon has not that much elasticity, so to say, in the sense that once you reached a certain level, it breaks and it goes. So you need to be really careful on that. But we were able to do it because when I joined Ferrari, so in June 2000, Rory Byrne was the chief designer for Ferrari, had this intuition, and he said, I want to have this angle, which is named camber angle, campanatura in Italiano. Again, I'm sorry for the drawing. So if we see the car from rear, this would be the right wheel. this angle here, when you enter corner, changes due to the compliance of the system. So let's say you have an end of straight, and this is a real example. You have 6,000 Newton coming from the weight of the car and the aero force. And then you enter a high-speed corner. So you have weight transfer from left to right, if we assume that this is the right wheel from rear. So you increase the vertical load, and you start rising a lateral load. You have a friction coefficient which is bigger than 1 for those kind of wheels. And this clearly is changing this angle. And you might have the situation where the vertical load is going to negative camber, and the lateral load is trying to push it on the positive side. It's clear that this variation of the angle is changing what is happening at the tire patch. So it might be that for a two compliant system, the tire is not working in the proper way. And the idea from Mr. Byrne was, I want you to check. It was for me because I was dealing with suspensions in Ferrari. I want you to check what is the angle here at the end of straight and what is the angle here in the cornering. So we found with the Reiko Dynamics guys, we found the condition on the track where this was happening, and it was the circuit from Barcelona before they changed to the chicane, so end of straight there. And she said, I want you to have this angle, this value. So you have this one minus this one, you have to halve it. How? Okay. Using simulation. It was not called simulation at the time. But placing everything together. So monocoque for the front, gearbox for the rear, suspension elements, upright, hub, and wheel bearings as well. So I built up, this was a summary of what I found. So we were looking also at the stiffness in bump, which is the vertical displacement, and in toe, which is the convergence of the wheels, but focusing on this one. These two were just side effects. And this basically is a sort of summary table where we see that the most compliant part, so the lowest stiffness, was coming from the wheel bearings. And there is not that much you can do because there are parts which are bought by supplier, SKF at the time. Then the second would be the upright. Okay, here we can work because it's a part that we are producing. And then you go to wishbones, so the suspension elements, and monocoque, and then back again to the hub. Plus, I have other parts which are not really relevant here. And I had sort of the total freedom to communicate to designers that up to the year before were trained to, okay, sorry, this one should have gone before, just to show that those elements, the flexures were made of carbon like that. So again, 24 plies, more or less, with the differences in thicknesses of 0.2 for the weaves and 0.14 for unidirectional fibers. Up to the point that, sorry, the designers were trying to take out as much as possible, as much mass as possible. So lighten, 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 because a light car can allow you not to be quicker because there is a minimum weight that you have to fulfill on the regulations. But if you are below the minimum weight, you can put ballast, and you can put ballast wherever you want. So the lighter the car is with respect to the regulations, the more ballast you can add, and you can put this ballast in front, at the center, on the rear to balance the car. So this is the real stuff in having a light car, because, as I said, regulations, you have to fulfill a minimum weight. And so we worked on everything, even on the bearings with SKF. And I'll show you here a model. But the funny thing was, I was going to the designers and say, hey, listen, this wall thickness has to be bigger because it calls for strain energy. So it means that it's used, so we need to put material. And they could not believe. And Rory Bell said, we go this way, we go this way. And in the end, I'll tell you, cutting a long story short, I think for every corner of the car, we added like from 2.5 to 3 kilos. So in total, let's say from 10 to 12, which is a lot on a Formula One car. And spraying mass, which is even worse. And yeah, that car, the 2001, was one of the quickest. And there is also a funny story behind that. Before starting this all this process, Rory Bell said, okay, we take an old upright, which at the time were made out of titanium sheet metal, so welded. And you tell me where to place some additional plates to stiffen it up. I could only reach 10% more, which was already something. And then they'd gone to test with Schumacher in Fiorano, only on the rear. And after the test, they asked the impressions from Schumacher because he was a very good test driver. Thank you. He was a very good test driver, and he said, "I don't like it. It's too snappy. It's moving too much. It's too nervous." And the track engineer said, "Yeah, but look at the timings. You are here." He said, "Yeah, but I don't like it." When Rory Byrne heard that, said, "We don't care. It's because we did it only on the rear. If we do the same thing on the front, it will be balanced." And actually, this is exactly what has happened. And again, here working on the bearings, because at that time it was not really possible to model the sphere or the balls. I would not recommend it even in our days. I substituted this ball with a nonlinear spring, which clearly makes some approximation because it cannot move like actually the ball is doing into the rollers. But this was not important to determine the stiffness. And coming up with something like that. So here there is just a comparison between the stiffness of a ceramic ball and a steel ball. Ceramic has a Young modulus of 300 gigapascal compared to steel, which is 200. So it's clearly a benefit. Of course, being stiffer, the imprint is smaller, so the contact pressure is bigger. And another funny story, when I joined Ferrari, they could not run ceramic bearings at the front because they were not lasting, not even 300 kilometers, so they could not risk to run it into a race. But with all the work done in stiffening up the upright, the hub, working on the bearing, suddenly the ceramic bearings were lasting not forever, but for sure with enough margin to run it in a race. So this was another side effect, and which was calling for more stiffness because ceramic is stiffer than steel. And here you can see the forces on the balls. Inboard is blue, outboard is red, starting from just the preload, because the wheel bearings are preloaded to reduce all the plays inside. And also there is a procedure to get the correct preload. And then on the straight there and on the corner here. And you see that on cornering, the inboard bearings, all the balls, the outboard line is 0. They're losing contact. They're losing pressure. And this is what is giving hard times to the rollers because the ball is in contact, then it comes out of the contact, and then it hits again back in the contact, producing some pitting. So here what you can do is either change the load line with respect to where the load is introduced. You can move the bearings, but this is something that has huge impacts on the design, or you can increase the preload. And this one as well might have some problems because there is a curve given by bearings manufacturer where you have a maximum in terms of lifing. So if you go too low with the preload, you lose mileage. If you go too high, you lose mileage. So there is a little margin where you can play to try and reduce that, or you can decide to live with what is happening. If the bearing survives, of course. And this here was done as a simulation to test what was really happening. So this part is a dummy upright with a real hub, but this was used to be placed on a test bench and checked. But if you look at here, the inner roller of the inboard bearing, this is inboard and this is outboard. You see the radial displacement, you have almost 0.2 positive and more than 0.2 negative. So you have almost half a mil of deformation there. And clearly this is coming also from the fact that the hub here might be too thin. So increasing this will also help reducing the deformation on the rollers. And finally, we tried to go also not into the tire, but into the rim. But to stiffen up the rim, we needed something to really introduce the load in the proper way. And with the tire in between, it's difficult. So we got the model from Bridgestone, very rough. Properties there were average properties, so they didn't want to release or to disclose information on materials. They gave us an equivalent material. I tried to run it at that time, so there was no problem to simulate the pressure inside and to simulate the vertical load. But as soon as I started to apply the lateral load, the model was not converging. Two big distortions on the elements of the contact. I tried with Abacus, with Nastran, Mark, I think, and no way. And the funny thing, when I was writing this book, I took exactly the same input file, and I ran it, and it ran. 20 minutes, 11 CPUs. And at that time, just to come to a give up, it was taking like hours. So I was running it before leaving the office and let it run during the night and whatever, and in the morning I always got errors. So this is to say that 20 years have passed, and a lot of development have been done in the pre and post-processing tools, but also the solvers have increased their capabilities because, as I said, the model is exactly the same. The input file from Abacus is still compliant now from what was written 20 years ago. I didn't touch anything, sorry. But very likely, I think it was running 16 or 32-bit software, and now I think it's 64. So probably now the solver can manage better the deformation of the elements. So even with distorted elements, you get a solution that maybe you need to investigate better. But still, it's a good progress, I think. And this was the result. At that time, we needed to test the tire, put some transducers there to get some displacement, and then find a way to introduce the load into the rim and to get the same displacement that we were having from the test. It was harder than having a model that was running. Oops, I'm too quick. The other thing that might be asked to a stress engineer in motorsport is optimization. Also, I don't know if you know Altair OptiStract, which is not Altair anymore, but this was coming out in exactly those years, 2001, 2002, for the topological optimization. So you get a design space, so where your structure can be. You have your boundary conditions, you have your load conditions, and you let the software run and say where he needs to put material to minimize the overall strain energy. This is giving you the optimal structure. And it's doing it for multiple load cases. So what I tried here was to take that monocoque, somehow fill it up, again, somehow leaving the space for the driver and the driver's seat and the driver legs, freezing the connections to the engine and to the suspension elements, and running topological optimization for just the torsional, let's say. There are many requirements as we have seen. We have the load on the roll here, which then is transmitted to the monocoque, so you need also to check that one. You have the side crash, you have the front crash. There are many requirements that a survival cell like that need to withstand. Torsional stiffness is more for performance of the car rather than for safety. And this is what you get. So the topological optimizer would tell you you have to do a monocoque like it was done before carbon, so 60s, 70s, like a tubular frame in the end, which is interesting on one side. Then you do, of course, you extract what the topological optimizer is telling you. You reapply the loads, you check for stiffness and stresses, and then clearly this structure needs a good designer to be designed and produced. And so I tried also a different approach. So following the suggestions from the topological optimizer, I said, why not having a boxed structure which can still be built with rapid prototyping, and place sheet metal more or less where the topological optimizer was telling me to place material, and then run a size optimization. So changing the thickness within a minimum or a maximum with continuity. And this is something that before the rapid prototyping took really importance in production, was giving hard times because you could not have sheet metal with continuous variation in thickness. You had to fix with integer variation. And this was again giving some interesting results, because compared to a very rough composite structure with high modulus materials, so with the strongest allowed from the regulations, the weight to stiffness was in favor of the boxed structure, meaning that maybe carbon is not granted to be the best for this kind of structure. Clearly, you also need to have a machine big enough to contain this thing, which is probably still not yet possible. But it would be something to consider. Of course, there are other disadvantages, because this cannot be really repaired. If you hit a wall, like sometimes it happens, and you might deform these parts, it's difficult to hammer it back to the right position and still be sure that it's safe enough. Carbon as well, it's a problem because carbon fails, but you can somehow more easily repair it by adding again plies, cutting out the portion which is damaged, substituting. Not a nice thing to do, but it's still possible. So this would be something interesting in the future to see if some teams might decide to go for this approach. Other thing that a stress engineer can be required to do in Formula 1 or motorsport is to analyze failures. So you had maybe some failures, and that were not expected, and so you need to investigate more. So here, for example, here is the rear top wishbone of a Formula 1 car. It's not this one. This one is here just to show what is the position. And there is a flexure there. So different philosophy than how Ferrari was building it, but still a shell model, which was giving a quite high, I don't see that, reserve factor. So we were confident enough that the shell model could have survived. But, so sorry, that the part calculated with the shell model would have survived. But actually it didn't. And when it was placed on the test bench, just with up and down, plus some forces acting, simulating running load, the travel was from -70 to +50 or vice versa, so not really big, but not really small at all as well. And this was the philosophy of the construction, the actual one. So this is the thick part, which is then bolted to the monocoque, and this is the flexure. So there are a lot of UVs, unidirectional, so stiff, and some cloths inside, plus closing ones to protect all these, which were otherwise ending to be visible and easy to scratch. And during the test, this part came off, so it's simply debonded. It started to debond, it increased. At a certain point, it stopped. So this was open. You could see this one was doing pumping, but it didn't progress. So it stayed there. It survived the complete test. So in theory, one could have said, okay, we go on the track. I guess that the driver, if the driver would have seen something like that, you drive the car, I don't. So I built up a 3D model. So each element is one ply to see the stress in the normal direction, because the shell model cannot. It's one of the limits. So shells are supposed to be thin, and this low thickness is assumed to have a sigma z, so normal to the plane, which is almost null. But when you come to certain thicknesses and when you come to transitions like that, a 3D model for sure is giving you better results. And indeed, here we see we go from -60 to +60 megapascal, which for a resin, because normal to the lamination ply, you have only the properties of a resins, there is no fibers along this area. There is a technique which is called Z-pinning, but is forbidden in Formula One, where you place some things normal to the lamination plane, which prevents this opening. 60 megapascal is by far too big. The funny thing was that the previous year was very similar. So this ramp was slightly smaller, and the excursion, the travel of the suspension, was smaller. So these two things together were enough to rise these stresses to the level where it failed. Also, this one I did it later in the past, so simulating again the bonding of these two plies with respect to the rest, and you can see, this is it's a plane cut in the middle, you can see that indeed it's happening, opening the plies, and it doesn't progress, because probably, very likely, when you come to a certain point, the sigma z gets below the lowable of the resin, and so it stops. Not nice to see. So I did the same thing for the old model and modified the new until I got to the same stress level as before. So reasoning by comparing could give a design change, which then made the parts to survive. And then you have also wings. They are more important now, as we were saying before. Wings are more important than any other mechanical part on a Formula One car, unfortunately. So the process is done there. You have the CFD department. What is the acronym for CFD? It's color for directors. Sorry, bad joke. You get a pressure distribution. So you take a pressure distribution from the CFD model, which is definitely much finer than what you get from the structure, and you interpolate it on your structural mesh. So here is a rear wing. This thing here is to activate the drag reduction system. And it's from 10 years ago, this car, so it's quite old. And you check the results, and you suggest for mass reduction, if possible, strength. You need to check also for local instabilities. And in theory, you should also take the deformed shape of this. You should pass the deformed shape to the iron department. They should remesh and recalculate the pressure distribution on the deformed shape, they should give you back the new pressure distribution, and you should iterate this process until you stay below a limit that can be chosen. It's not all the teams are doing that. And then when you see on the track how on the camera cars how wings are vibrating, I start to doubt that they perform as they should, or as the CFD is saying, and as the wind tunnel is also confirming. Here is just it's not really a dynamic calculation. This is static, but it's done in order to try and find out what position during the DRS opening was giving the maximum stress to size, support, and all the elements inside, and also the actuator there to know what the force is required. Sorry again. The information there is required by who is designing the piston, of course. The World Endurance Championship also, very different cars. They need to be fast, but they also need to be strong. They need to resist maybe 6 hours or 24 hours in Le Mans. So it's a slightly different approach than Formula One. So here we see a rear end with the diffuser, with the rear wing is still half, and the front. This is interesting because it's coming from Porsche. So when in 2017 they decided to abandon the championship, they wanted to give to the car and to the people working on the car the possibility to do something more. So they said, okay, we get rid of all the regulations. So we ignore the regulations and we do whatever we can to make the car as quick as possible. So they introduced the DRS on the rear, which was not allowed by the regulations. And they wanted to do it also on the front. But the rear is easy because you have a flap and you move a flap rigidly. The front, there is no flap. So they wanted to have a sort of flexure again in the trailing edge to allow this to move. And this was the interesting part. Because, of course, you cannot place a hinge in there. And we did it virtually with some rubber layers in the middle of the laminate, and also some very thin pie laminate to allow for this. Clearly, you have the displacement, and you need to be stiff enough not to have a shear movement of the trailing edge, and the stresses have to be clearly below the level. In this case, the deformed shape was passed back to the CFD guys to check what would have been the drag reduction coming from this movement of the trailing edge. Here is again the VEC. It's on a LMH car, French one, which is also Italian. Maybe I should not say. Again, front end, different, somehow same concept with the wing with no flap on the front. And this was just to show that finite elements are fantastic. They give you tons of information. And sometimes, maybe more often than what is shown here, you still do some hand calcs because it's anyway a good approach. And you do it maybe based on the information you get from the finite element model, like in this case on these hooks which are connecting the wing to the flap. So the software can integrate the stresses on the section and calculate for you the section forces like that. And then you can do your calculations, and sometimes for a quick information, say, okay, this is failing. What is the new section I might have there? You cannot clearly rerun the finite element. You do that in 10 minutes and you can get an idea on how it needs to be done. This is the same car, rear end. As you can see, models now are the elements are much smaller than the first one I showed you. because clearly computational time and meshing it's much quicker. And here we have another failure criteria, the one from Zaifu for composite part on the rear end. And here I wanted to see what could have happened in a bird strike. It's not so uncommon. Alonso in Formula Indy has killed 2 pigeons, I think. They were just running on the track and they are vaporized. This method is quite recent. It's the smoothed particle hydrodynamics, where your bird-like object is modeled with the particles. Indeed, you give the density and the properties of the material, and there you run an explicit analysis, like for crash tests, where your bird-like object it's just split into some parts, and the wing is clearly failing here and there. It was just an example. FIA is not requiring any of these calculations so far. Formula E, they are also running interesting things. They don't have that margin to work because it's a more or less a mono product part, but there are some parts where the teams are free to work, like rear suspension. And what you see here, it's a super element. Substructuring was used because this part is containing the engine and the inverter, plus it's not really a gearbox, but it's a reduction. And it's made out of carbon again, and this was developed by another company, and they didn't want to give us, or me in this case, the information of how they built it, which is fair enough. So we agreed on where we can reduce their structure to the points, the connection points, and the constraint points to the monocoque and to the suspension element. I was in charge to size and check the suspension element. This is a push rod. It's the one which is, during the movement, activating a part here which is called rocker, which rotates, and it's connected to a damper, spring, anti-roll bar system, and whatever you can imagine to place in that car. And what we see here, it's the comparison from just the vertical load with the fixed model, so considering that those points are constrained to ground, compared to what we have with the super element. And you can see that we have, well, maybe it's not really that visible, but if you check this point, for example, you see it's moving quite a lot. This is 20, the scale factor is not really a lot in absolute sense, but enough to affect those camber stiffnesses that we were discussing about. So this suggested to modify somehow the drawing, the design of the casing where this is attached to stiffen that point up. This is the part, as I mentioned you, is the rocker. This is somehow the insert, metal insert, which is embedded into the carbon casing. This is where the push rod is connected. So this one is pushing when the suspension is moving. Here we have the damper, and here the anti-roll bar system. This one is just to show you what is happening. The system is very complex, was very complex. This was one of the first attempts. This is scale 1 because it's a nonlinear analysis, so you need to be careful in amplifying the deformations from a nonlinear analysis. And you see that here there is a bolt which is modeled with a beam element, which is preloaded, trying to clamp everything together, but when we apply the load, you see that this is opening. And this, again, is not good for different reasons. For compliance, but also having a hit there would have worn out the insert, and then this is a problem because the insert is inside the casing and you cannot replace it. What you could do would be to maybe weld something on, and welding aluminum is not the nicest thing. Brake pedal. It was supposed to be out of carbon, then they decided to go for aluminum for safety reasons and being more confident. The The thing is that when you have to deal with human beings, like brake pedal is activated by human beings, what is the load that you apply? Where is applied? So you have the footprint somehow, but every single might push a little bit more with the toe, and some other maybe with the center, and the force. I remember when I was in Toyota, and we had the telemetry data from the pressure in the system, in the brake system, Jarno Trulli was pushing almost constantly 140 kilograms. And in hard brakes, he could reach almost 200 kilograms. And the guy is weighing, I don't know, 70, 65, 70 kilos. So it's really pushing against also the seat. And yeah, there is no rules in here. So everybody is doing what they think is sensible, but it's clearly something dangerous. I mean, you cannot really fail brake pedal. And then we have hypercars as well. A lot of people in our days would like to build their own hypercar. And this project was supposed to be an electric car, which should have also, the intention was to break the record from Porsche, the Porsche we were seeing before, at Nürburgring, that track. Fully electric, we were in charge of the suspension elements. So this one is again called a rocker. It's similar concept of what we see before, but clearly we have a lot of other things attached to do. We have transversal damper, a transversal spring, a mass, moving mass, the so-called inerter. And the model here is still non-dynamic, is static. It's done to check where what is the position with the maximum stress among all the load cases. That one was the front, and this one is the rear, I think. And yeah, we use that one to check for the stress level. Very rough model, so very coarse mesh, just to get the position where we have the maximum stress, and then we have frozen that position and realized a very detailed model to calculate the stresses. And again, same car. They were not asked to comply with any rules because the record lap would have been run on their own, so no other cars. But they wanted to comply with the Formula One rules. So this is the halo, the one you have in front in the Formula One, which is made out of metal, I'm sure. They wanted to have it in carbon. So again, here you have two tests. One is from the side, one is from the front. It's bolted to the monocoque, and we sized that for them. And a similar thing for the rear, the roll loop. Again, this is bolted and bonded on the feet, and they wanted this one to comply with the F1 rules. Again, wings for hypercars. I think this was a aftermarket part for Lamborghini. Nothing really special in this case. They are super safe. They don't care too much on the weight. This was another hypercar based on the C4, Alfa Romeo C4 monocoque, and they built their own parts. This is just to show how complex it is. This is core or foam, and you have carbon inboard and outboard, so inner skin and outer skin. It was a quite challenging stuff for the realization of the model, but not many really interesting things. They wanted also to comply with in this case, the LMP1 rules for the Le Mans car, which was quite harsh, especially for the crusher. They wanted first of all in carbon. They did a test. It failed with respect to the regulations, so they had higher peaks of acceleration in an area where it was not allowed to. And then they gave up on that. They reverted to aluminum, but again, they made it wrong because here they didn't do any buckling calculation, any instability calculation on the crusher itself. So they failed again. Then they asked us again to redo that. We found this problem, and the quickest thing was to increase just by a little bit the thickness of the walls to make it stable and run the way a crusher should work. I think that's it from my side. Yeah, we leave this one. Too long, too short?
No.
It's
you want, you have also time. If you want to add something, there is time, otherwise there is no question.
Yeah, exactly. I wanted to ask. I let them maybe.
I think that's a question.
Even if I met Schumacher in my life.
What's the problems on Ferrari?
Maybe we can talk for another couple of hours.
Two problems, 2 or 3 problems of the in our fields. I still have friends there. They are working. Some of them are still in the F1 department. Most of them have been moved to the back, and they will. This is one thing. I think the biggest problem happened in 2014 when they changed. Marchionne wanted to get rid of many of the old guys. My former manager there was one of the victims, and he was not moved to the other department just to out. Being a manager, it was easy to get rid of him in this case, but also other experienced people. I mean, he is 9 older than me. So at that time, he was still not so old, really not young as a just graduated guy. But the problem is, you need to be quick in Formula One, this is sure. So a fresh brain is for sure something we need, but you need also to guide the fresh brains. And getting rid of these people, those people you got rid of all, or most of the experience. So probably they started running into the same pitfalls that they would have been avoided if someone else would have told them, listen, this doesn't work. And this is one thing. So there is the needing of rebuilding up the experience, and it's not something that we do in 1 year or 2 years. It takes long, maybe not as long as it's taking now. Then the other thing, you need to have someone on the really top that believes and wants you to do things, because Formula One, you need money. This is necessary. It's mandatory to have money, but it's not enough to have money. You need also to know how to spend them. Toyota is a clear example of that. We were, unfortunately I was part of it in that time, we were the team which was spending more than all the others and scoring the least points in the championship. So you need how to place where, what is important and where to spend. And you need someone, as I said, that wants to achieve something. Luca Cordier might be not really seen as a nice guy, but for me, it was the right guy at that time. And he was really motivating. After each race, or every 2 or 3, we were having a sort of briefing with all the company, and he was speaking, and you were coming out from that speech walking 1 meter from ground because you were really feeling motivated, and you were working long times because of that, and you could see the results. And then by seeing the results, you were pushed to do even more. And he was able to build a team. He wanted Jean Todt. I might have something to say, but he was the right person again at the right place for the time being. And in turn, they then acquired Schumacher. He wanted Rosberg, Ross Brawn, Nigel Stephanie, so few key people. And basically, this is what you need for success. You have good engineers that are well guided from people, and you have money to spend in what you think is important. Schumacher clearly was one of the key factors because he was the best driver at that time, a good best driver, and he could help to develop the car. Then there is also, of course, part of luck, because sometimes when you change the regulations, you don't know exactly where you end up. Especially because aerodynamics is still a huge variable. There are not clear things for there are, but they're not so strict like for structural analysis, where you know that by increasing the section by 1 mean, you reduce the stress by X level. So there are many things there. And I think at the moment it's more political, not in the sense that with internal policy, politics. And I don't think that Elkan is really someone interested in having Ferrari win something. And if you don't have that, no. Things might change, could be, but I see it very hard. And on top of that, I know Vasseur, because I was at Sauber when he was the team manager at Sauber. So he is not really the guy that could rise the team from that point. Not in quick times. And for sure, he's not in a good position from his side. I mean, he might get some pressure on the top, no results. Let's see, unfortunately.
From your experience, do you think that rapid prototyping makes the design of components easier or more difficult? In a way that it has to be rapid?
It's easier in the sense that you can obtain shapes that you could not achieve in the past. I have an example of that in Toyota. We tried the topological optimizer on a rim, and without thinking that we should have placed some constraint on the topological optimizer, and what he built up in the end was something with the spokes which were hollow. And at that time, the rapid prototyping was only plastics. So we could not say, okay, we build it in metal with rapid prototyping. So you can have shapes that you didn't have before, and it's more difficult because you have to consider the way it will be produced during rapid prototyping. So you need an expert as well in understanding what is the best positioning of the part inside the machine to get the best structure you want. And it makes more difficult the fatigue calculations, because the hollows that you have inside cannot be reached to final treat the parts, to polish it or sand it or whatever. So you have a very rough material inside, and the lower the fatigue are very low. So you might find that your part is completely okay when you look at it from the outside, which is what we are used to, because higher stresses you have in general on the outside part. Then you need to look also inside, and considering that lower stresses can be a problem because you have a lower and lower body, especially in terms of fatigue. So it opens more possibilities, but it constrains you to be more careful on some things. But it's the future, so we have to do that.
You mentioned your experience in sending the CV by one company. What's your suggestion now what to do for entering in a company like that, not in automotive, but in general, a big company that uses topological analysis and this stuff at high level?
You need to find what are the companies that more or less all of the medium to big do have. Maybe not a department which is doing all of that, but they have maybe the tools. So you might enter as a designer, doing the design, but also doing the calculations. So aerospace companies for sure do have a good platform. Automotive also, and some other big ones that don't have any particular in mind. But it's the CV. It's a long time that I don't send my CV. I don't know really. I think internet has opened a lot of possibilities. Of course, you have, but then you also have a lot of competition in the sense that you are not one which is really highlighting yourself, so you are lost in many others. I would suggest if you want to do that, you need to do all the courses and trainings that are involved in this. So simulation tools, not really learning a special tool. It's not the required. If you know abacus, you can use ANSYS, maybe, or Altair, or vice versa. You need to know the method. That's the approach, the things that you have to do. And then, depending on the tool that you get, you will find the way to do what is necessary to do. It's more confusing, you know, maybe because I'm getting old, of course. And changing from one tool to the other is not so easy for me now, but I have some students who think that it's easy. So I do believe that you are able to do it. It's more like anything with the this is why the method is more important than the software itself.
Question?
Which is the most valuable lesson that you have learned during your long career?
Never trust your results. Never trust your results, and never trust your results at the first time. Always think. Analyze your results with criticism. Think at your intuition, which clearly, when you start working, is based on not nothing but only what you've studied. And you grow up your sensitivity to what might be wrong or correct at the first time. But despite this, after 33 years of doing this jobs, I do mistake as well. The good thing is that the first I'm looking at the result, no, it doesn't really sound like it should be. And you have to listen to that. Even if then you prove that your intuition was wrong and the calculation was right, but you have to follow what your intuition is saying. Because 99% of the cases it's correct. Engineering judging machines are stupid despite the artificial intelligence, they still are stupid. So they give you the results based on what you give them inside. And nowadays, calculations like that, with the explicit approach, you cannot really, you can do a backing analysis, maybe on that, no, but you need to know what is the force. And to know the force, you either have to test it, to see how the force is developing, or calculate it. So you have to rely on those more and more, and so you need to be sure that the way you build your model is right.
Question? You mentioned artificial intelligence by not being so concerned. Do you think we could use it in a way in central mechanics, or it's a bit too early?
It's a tough question, this one. I tried to take the free version of ChatGPT, and I have asked him because I live in Switzerland. I asked him what is the southern point of Switzerland, and he was wrong. Really wrong. I asked him if he could write the input file, raster input file for a cantilever, the simple one. And caster, clamp, defaults. He said yes, and then he didn't do it. I think, like all the tools, they need to be used knowing the limits they do have. I'm seeing a lot of posts on LinkedIn saying, hey, look what I was doing. I ran 12,000 of CFD analysis, and then AI gave me the best shape based on those results. But those results might be wrong. They might be artificial. And so the answer, which should be the synthesis of all these results, might be wrong because the input is wrong. If you tell me that structure is calculated completely by AI, I would not jump on it or say no, or I would, before seeing more details, so to say. No, it's completely AI based.
Think about the AI-based design, which is then validated using
Yes, this is okay, because the human being is still the one which has the final word, so to say, on what is produced by an expert system like they were called in the time.
It's more a problem for designers than for structural engineers. A structural engineer is more future-proof.
It depends, because sometimes it might happen that the designer decides to not ask the stress engineer to check his structure. Also, this one is things that should not happen, but sometimes they do. So he might have calculated everything with an intelligent tool, and then doesn't ask you because he is confident that it's right. I have an example of that before the AI time in Zagor. We overlooked completely to a pressure vessel inside the car. I don't remember if it was the driver, drinking system, or whatever. I don't know. We didn't have the time, and the designer decided to use the finite element tool, which is inside CATIA and FIMI. At that time, it was that one. Now it's also Abacus, because Abacus has been bought by Dassault. So he did his calculations, then we didn't know anything, until the point that from the testing, luckily, this tester, it exploded. Then we were involved. Who did the calculation? Him. Not pointing the finger, but at least we asked him what he did. So he showed us his model, and it was like an element like that, so big. And we asked him why the mesh is so close. And he said the answer was because if I was making it finer, I was getting higher stresses. and as this happened, yes, we were acting like that, but we lost time, money, because of course the thing was built wrong, tested it, we had to recalculate it, reproduce it, and retest it. Yeah, and this, but why didn't you ask? You were so busy, okay, but this was a 5-minute question that we could have answered. It was not the complete calculation that we were asked to do. So, yeah, so this is why it would be anyway dangerous, because the designer could say, okay, it's calculated by artificial intelligence, so it's fine. Might not be.
I have a question. Are these rapid prototyping methods that you described deterministic or based upon some kind of AI that tries to find the best shape for the purpose?
The topological optimizer. No, that is not AI based. It's just simple, so to say, maths, in the sense that you get this design space, which is where your structure can be, and you give the properties of the material that it's supposed to be built with. And then he runs iterations, checking for the strain energy, and where he found low level of strain energy, he changed the, how do you call the stiffness density. So he reduced the Young modulus of those elements to a very low level. So the elements are still there, but they contribute less to the next iterations. So sometimes some of the elements that got low density at the beginning, they come up again. And you can check all the iteration he does, and you can see how he's developing. So it's pure mathematics. No artificial intelligence.
Given the same data, initial data, will
produce the same
result.
Yes. Okay. Unless some numerical round off, maybe running on different machines, like when you run nonlinear calculation, you might end up with slightly different results depending on the version of the software and on the machine where you have run the calculation.
How much is the competition expensive to do this kind of things?
It depends on the dimension of the model. Clearly, the thinner you go with the element size, the longer the time, of course, but the better the representation of the structure will be. So you need also to compromise, and here is again where the experience of the stress engineer is coming into the game. Decide the best compromise between computational time, which computational effort, which means also time, and quality of the results.
Any other question? I have one. I recall in one of the subjects we have been written about variable amplitude loss fatigue. About the load spectra for Formula One race car. They are taken from the literature, or are you developing experimental tests for getting? And then I suppose that the car has a different load spectrum with respect to Monza or the other circuit. How did this that with the teams?
To be honest, when I started in Ferrari, fatigue calculation was not really done. But there is a reason why. Because the parts were substituted more or less every race. Because at that time, there was no budget cap, so everything new for each race. So maybe 500 kilometers on each. So they were not really fatigue. But then we started, they were tested. This was short. They were tested, especially the carbon parts, the wish ones, they were tested in fatigue. But basically, it was taking the 80% of the highest load case that we had static. So just saying this is static, so it's a limit load, so to say. And for fatigue, we say it's 8%. So it was, I think there was a reasoning behind looking at the telemetry data. So you get the envelope from telemetry, and this is your design loads, and then probably checking what was the difference with running loads. You were getting your effects. Monte Carlo had special wishbones, especially for the steering rod. You made a high angle, so this was changing. And you had a reinforced steering rod and track rod at the rear because hitting the barrier was more common than other tracks. More recent times, we based again on some assumption, reducing the design loads, and you do calculation like that. Maybe these belts, hubs, which you anyway see some 1,000 cycles, even on short mileage, you do that. But it's not really a real issue with static, self-factory getting static, which is not that high or that low. Sometimes with 125, some feel better with 1.5, and this giving again the number of cycles that you see, it's enough to cover also.
Okay.
I know you're looking at it very close. Yeah.
Okay. So now thank you again. Very interesting presentation, and now we stop. You will meet at Dr. Iliad in 1 hour and a half, I think, and then we will meet again on Wednesday, 8:30, L07. Okay, not the usual room, but number 7. Okay, thank you. Un sacco di domande, quindi posso dire che
Sì, infatti ho voluto fare
no, hai fatto bene.
perché la formula hai detto come esco qua, questo, leave me.
Vai.
Oh mamma.